One more important theorem. Prove that a finite non-empty complex H of a group G is a subgroup of G if and only if A comma B belongs to H gives AB belongs to H. Only one condition, closure property is enough for a subgroup if H is finite. Very, very important. H is a finite non-empty complex. Non-empty complex means a subset, non-empty subset. Already we have proved H is a subgroup of G if and only if two conditions. A comma B belongs to H gives AB belongs to H, closure property. A belongs to H gives A inverse belongs to H, inverse property. Two conditions, closure and inverse if and only if H is a subgroup. Here H is finite, only one condition is enough. Very, very important theorem. Proof, let H be a finite non-empty complex of a group G, non-empty subset of a group G. Part 1. Part 1 is necessary condition. Suppose H be a subgroup of G. H be a subgroup of G, we have to prove that A comma B belongs to H gives AB belongs to H. Since H is a subgroup of G, by definition, H is itself a group with respect to same operations of G. Since G is a group with respect to multiplication, then H is also a group with respect to multiplication. Since H is a group, H satisfies four conditions: closure, associative, identity, and inverse. By closure axiom, A comma B belongs to H gives AB belongs to H. So necessary condition is verified. The part 2, this is sufficient condition. Suppose A comma B belongs to H gives AB belongs to H. It is denoted by equation 1. Now we prove that H is a subgroup of G. H is a subgroup of G means H satisfies two conditions. A comma B belongs to H gives AB belongs to H is the closure property. A belongs to H, A inverse belongs to H. This is inverse property. The two conditions enough for a subgroup. Already we have proved the very, very important theorem. H is a subgroup of G if and only if it satisfies two conditions. It is enough to prove that inverse element exists. Every element in H having multiplicative inverse. Already closure condition exists. A comma B belongs to H, AB belongs to H. Equation 1. Inverse axiom. Let A belongs to H. A belongs to H. Replace B by A in 1. A comma A belongs to H gives A into A belongs to H. That is, A belongs to H, A belongs to H, A into A belongs to H. A into A is A square. A square belongs to H. Again, A belongs to H, A square belongs to H. A into A square also belongs to H. A into A square is A cube belongs to H. This is A belongs to H, A cube belongs to H, gives A into A cube also belongs to H. This is A power 4 belongs to H. Similarly, we get A power 5 belongs to H, A power 6 belongs to H, and so on. A power m belongs to H, and so on. Similarly, we are continuing in this way. We get a set H is equal to A square, A cube, and so on, A power m. These are all infinite in numbers. Since H is a finite set, given condition, H is, then there must be some reputations exist in the elements of H. That is A square, A cube, and so on, A power m, and so on. Suppose two elements equal. A power m is equal to A power n for any m comma n belongs to n and n greater than m. It is denoted by equation 2. Two elements equal. A power m is equal to A power n. Both sides multiply with A power minus m. A power m into A power minus m equal to A power n into A power minus m. So A power m minus m, since A power m into A power n equal to A power m plus n. Here minus A plus of A power m plus of minus m, m minus m equal to A power n minus m. A power m minus m is A power 0 equal to A power n minus m. A power 0 is E. Very, very important. A power 0 is E. Since A power m belongs to H, A square, A cube, and so on, A power m belongs to H. Since H is subset of G, all the elements in H are the elements in G. Since A power m belongs to H, A power m belongs to G. Since G is a group, G satisfies inverse condition. So A power, every element in G having multiplicative inverse. So A power m inverse also belongs to G. A power m inverse is a power minus m. Since a power m whole power n, this is equal to a power mn. So a power minus m belongs to G. So a power m belongs to G, a power minus m belongs to G, inverse elements. We know that A inverse equal to A inverse A equal to E. Therefore, a power m into a power minus m equal to E. A power minus m is the inverse element of a power. A power m minus m equal to E. A power m minus m is a power 0 is E. E is the identity element. A power 0 is E. Very, very important. So it is denoted by equation 3. It is denoted by equation 3. Since n greater than m, m and n are natural numbers. N greater than, suppose 4 greater than 2. 4 greater than 2 gives 4 minus 2 equal to 2, also greater than 0. So n minus m also greater than 0, positive number. N minus m is a positive number, so that n minus m belongs to n. So m and n are natural numbers. M minus n is also a natural number. So n minus m belongs to n. Since n is 1, 2, 3, 4 and so on, that gives n minus m is greater than or equal to 1. Greater than or equal to 1. 1, 2, 3, 4 and so on. So n minus m minus 1 is greater than or equal to 0. So m greater than or equal to 0, a power m belongs to h. All the elements in h are the integral powers. So that is a power n minus m minus 1 belongs to h. Therefore, a belongs to h and a power n minus m minus 1 also belongs to h. Using 1, a into a power n minus m minus 1 belongs to h. Now, a into a power n minus m minus 1 is equal to a power 1 plus n minus m minus 1. Since a power m into a power n, this is a power m plus n. So 1 1 cancel, that is a power n minus m. Using 3, a power n minus m is equal to e. That is a power n minus m is e. Again, a power n minus m minus 1 into a. That is equal to a power n minus m minus 1 plus 1 and 1 1 cancel. This is a power n minus m is e. Therefore, a into a power n minus m minus 1, that is equal to a power n minus m minus 1 into a is equal to e. We know that a dot b is equal to b dot a is equal to e gives b is equal to a inverse. That is the inverse property. So here a power n minus m minus 1 is equal to a inverse. So a inverse. So a belongs to h. A inverse is also belongs to h. A power n minus m minus 1 is the inverse element of a. That means every element in h having multiplicative inverse. Satisfying closure and inverse, then we say that h is a subgroup of G. This concludes that h is a subgroup of G. Here observe, h is a subgroup of G if and only if it satisfies two conditions, closure and inverse. Hence proved.